So today we're going to talk about factoring. We need to know how to factor in order to solve polynomial equations. So this little chart here gives us some factoring techniques for a few of them that we already know and a few of them that we're going to learn today. We already know how to factor out a greatest common factor. We already know how to factor a quadratic trinomial. With the example, we already know how to factor perfect square trinomials, which are basically quadratic trinomials, same thing. And then we also know how to factor the difference of two perfect squares. So those are the types of factoring we reviewed last chapter. Today, we're going to learn how to factor by grouping and how to factor the sum and the difference of two perfect cubes. So let's talk about grouping first. So we're going to start with number 3. Number 3, notice, number 3 has 4 terms, just like this example up here. 4 terms with no greatest common factor. So 4 terms where all 4 terms do not have a greatest common factor. That's when we know we're going to factor by grouping. So what we want to do is make two groups of 2 terms. Each group has 2 terms, where each one of those groups has a greatest common factor. So I'm going to factor out an x squared from the first group. And when I do that, I'm left with x minus 2. And then I'm going to factor out the greatest common factor from the second group. So I'm going to factor out a negative 4. And when I do that, I'm left with x minus 2. So I want you to notice that the stuff inside the parentheses is exactly the same. That's what we want when we factor by grouping. So the next step is to make 2 binomials. The first binomial is that x minus 2 that the 2 terms have in common. And the last binomial are the 2 GCFs you factored out. And that's how you factor by grouping. It's that simple. And so let's review that again. We made 2 groups where each group had a greatest common factor. And then I factored out the GCF from each group. And so that after I do that, then we want the stuff inside the parentheses to be exactly the same. So that becomes our new greatest common factor. So I'm going to take that out, and that's my first binomial. And then my second binomial is going to be the 2 GCFs that I factored out. And then I'm ready to factor again if I need. So I see x plus 2 times x minus 2. Okay, so we factor that. That's how we factor by grouping. Okay, so we can do number 4 also. Number 4 is exactly the same. We have 4 terms where no GCF, so I'm going to make 2 groups. The first group has a greatest common factor of x squared, so I'm going to take out an x squared, and I'm left with 2x squared. I'm going to take out a 2x squared. When I take out a 2x squared, I'm left with x minus 6. And then I'm going to take out a 5 from the last group. When I take out a 5, I'm left with x minus 6. So the stuff inside the parentheses is exactly the same. That's what I want. So I'm going to make 2 binomials. The first binomial is that x minus 6 that they have in common. The last binomial is the 2x squared and then the plus 5 that I factored out. Okay, so that's it. That's how we factor by grouping. Okay, so we can also factor what's called the sum and the difference of 2 perfect cubes. So a perfect cube is something being raised to the 3rd power. Something times itself 3 times. So we could make a list of the perfect cubes that we need to recognize. We need to recognize 1, 8, 27, 64, that would be 4 cubed. 5 cubed is 125. 6 cubed is 216. 7 cubed is 343, 8 cubed is 512, 9 cubed is 729. Don't worry if you don't know these because you're going to have a calculator. 10 cubed is 1,000. So these are our perfect cubes that we need to be able to recognize. And when we factor the sum and difference of cubes, we're going to use these 2 little formulas here. These 2 little formulas here. Get my highlighter. There we go. These 2 little formulas here. When it's the sum, it's going to be a plus b and then a squared minus ab plus b squared. So it's always going to be a binomial times a trinomial. So when it's a cubed plus b cubed, it's going to be a plus b, a squared minus ab plus b squared. And when it's a cubed minus b cubed, it's going to be a minus b, a squared plus ab plus b squared. So notice those formulas are exactly the same, except the first 2 signs are switched. So the a and the b are the 2 things being raised to the 3rd power. And we just have to know our formula. That's what we have to know. So let's do number 1, x cubed plus 216. So we're going to make a binomial times a trinomial. And the a is the x, and the b is the other thing. 216 is the same thing as 6 cubed, so the b is 6. So I'm going to write x plus 6, and then x squared minus 6x plus b squared, which is 36. And I'm done. So we're going to do the same thing again. 125x cubed minus 1. I'm going to make a binomial times a trinomial. And the a in this case is 5x, because 5x times 5x times 5x gives me 125x cubed. And the b is 1. So I'm going to write a minus b, so 5x minus 1, and then a squared, so 25x squared, plus a times b, so 5x times 1, plus b squared, so 1 squared is 1. And then that's it. So if we know our formula, our formulas, then we'll know how to factor the sum and difference of cubes. And also, and one more thing I want to bring up is the fact that this trinomial right here, these trinomials, they look like it's something. They look like it's something that we know how to factor. But these trinomials will always be prime. Okay. All right. So now we're going to review also. Sometimes we can factor a trinomial, but it's not quadratic. It might be quartic. So let's look at number 6. Number 6 is a trinomial that's not quadratic, but it's quartic. So when we have this situation, we can still do FOIL backwards, just like we were doing with our regular old trinomials that we know how to factor. But the difference is, instead of putting like an x times an x, we're going to put an x squared times an x squared to give us x to the 4th. And we still need factors of 6 that add up to 5. So I'm going to put a plus 2 and a plus 3. And I'm going to do the same thing. I'm going to do the same thing with number 5, because what I have here is I have the difference of squares, but it's not with an x squared anymore. It's with an x to the 4th, because an x to the 4th is a perfect square. X squared times x squared gives me x to the 4th. So I'm going to make two binomials. What times itself gives me x to the 4th. What times itself gives me 9, and I want 1 minus and 1 plus. So we've got the difference of squares, and we've got a regular old trinomial here. But the difference is we've got a quartic instead of a quadratic. So we can use this type of factoring in order to solve polynomial equations. So let's go to the second page, and let's solve a few equations together. Let's start with number 10. I see number 10, we've got 4 terms here. So I'm going to need to be thinking grouping, right? So I'm going to factor this by grouping. I'm going to make 2 groups, and I'm going to factor out an x squared. So x plus 6 left over, and then I can factor out a minus 4 from minus 4x minus 24, and I'll be left with x plus 6 there. So notice, remember, the stuff inside the parentheses is exactly the same. That's what I want. So I'm going to make 2 binomials now. The first binomial is going to be the x plus 6 that those two have in common. And then the last binomial is going to be the 2 GCFs I factored out. So x squared minus 4 equals 0. And remember, I always want to look to see if I can factor again. So x plus 6 times x plus 2 times x minus 2. So I set each factor equal to 0. When I'm solving an equation, remember, I factor, and then I set each factor equal to 0 to find the solutions. So my solutions are negative 6, negative 2, and 2. So we can do that again for number 11. For number 11, though, we're not going to factor by grouping. I think I see the difference of 2 perfect cubes. So my formula here is a minus b, a squared, plus ab, plus b squared. So I'm going to make a binomial times a trinomial. And so I'm going to write x minus 2, because my a is my x and my b is 2. And so then I'm going to do a squared, so x squared, plus a times b, so 2 times x, and then b squared. So that would be 2 squared, which is 4. And so remember what I said about this trinomial. This trinomial is prime, so we can't factor it anymore. So we're going to set each factor equal to 0. So this is the case where we get 2, but we also get a trinomial we can't factor, so we have to use the quadratic formula. So I'm going to say x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So negative 2 plus or minus the square root of 4 minus 16 is negative 12 all over 2. negative 2 plus or minus 2I squared of 3 all over 2. And the last thing we're going to do is reduce our fraction. So 2, 2, and 2 all divisible by 2. So I'm going to make this a 1 and make this a 1, and it's all over 1. So let's look at these two. The number 10, the degree was cubic, and I found 3 real rational solutions, didn't I? Number 11 was also cubic, and I found 3 solutions, but they're not all real, are they? 1 real rational solution, 2 is real and rational. But the other 2 that I found are imaginary, aren't they? So that happens sometimes. Sometimes we have 3 solutions altogether, but sometimes some are real and some are imaginary. Okay, we're going to do this one more time. Number 12. We're going to solve this equation by factoring. And I see one of those quartic trinomials I was just talking about, where I can factor it. I can do FOIL backwards. So I'm going to do x squared times x squared. And I need factors of 9 that add up to negative 10. So that would be minus 9 minus 1. And then I can factor again, difference of squares, right? And then I set each factor equal to 0. So I get negative 3, 3, negative 1, and 1. So notice, this time I have a quartic equation, so I found 4 solutions. And in this case, all 4 are real, and they are all rational. So the next 3 are exactly the same. We just factor, set each factor equal to 0. We're going to go do one more example about the candy factory. The candy factory needs a box that has a volume of 30 cubic inches. The width should be 2 inches less than the height, and the length should be 5 inches greater than the height. What should the dimensions of the box be? So I've got a box. I'm going to make a box here. I'm going to label my length, my width, and my height. So it says the width should be 2 inches less than the height, and the length should be 5 inches greater than the height. So I'm just going to call the height h. And so that the width can be that minus 2, h minus 2, and the length can be that plus 5, L plus 5. Oh no, I'm sorry, not L, H. H plus 5, the height plus 5. So now I know that the volume needs to be 30. The volume of the box is the length times the width times the height, isn't it? So I'm going to say 30 equals h times h minus 2 times h plus 5. And then I'm going to distribute. H minus 2 times h plus 5 is h squared plus 3h minus 10. Then I'm going to distribute my h. So I've got 30 equals h cubed plus 3h squared minus 10h. So we're going to subtract 30 from both sides, set it equal to 0, so that we can factor. So I'm going to factor by grouping. I'm going to make 2 groups, factor out the h squared, and then factor out the negative 10. Notice the h plus 3's are the same, so that's a good sign. So I'm going to write h plus 3 times h squared minus 10. And I'm going to set each factor equal to 0. So I get either h equals negative 3, or if h squared minus 10 is equal to 0, then we have to add 10 to both sides. Take the square root of both sides. Don't forget plus or minus. So we found 3 solutions to this equation, but remember, h represents the height of the box, and we don't want the height of a box to be negative, so we're going to say that the height has to be positive square root of 10. So if the height is the square root of 10, then the width would be the square root of 10 minus 2, and the length would be the square root of 10 plus 5. And those are all inches, aren't they? Inches.